Julius Caesar was not in his right mind. Okay? He was not feeling good. He was feeling dizzy. He was feeling anxious. He was not feeling good. Okay? He couldn't focus on things in front of him. He was seeing double. Has this happened to you ever? If you're feeling dizzy, you see double. He was seeing double. Brutus came to meet him. What will Julius Caesar see? Brutus. Because Brutus, you too? Some people get it. Okay. Later in the evening, Julius Caesar, after meeting Brutus, is really frustrated, really very angry. Now he's scared. He's very anxious. He's seeing Brutus everywhere. Everything he sees, he thinks it's Brutus. Brutus is coming to. He doesn't know yet. He doesn't know yet. Go watch the play. But he's very scared. Okay. He's lying at the top of the Parliament building. He sees two bright stars in the sky. But everything he sees, he thinks is Brutus. So if he sees two stars in the sky, he sees two Brute. Is Brutus? Brutus, you too? Okay, I have been told that we need to start with a funny story. So I started with a funny story. I'm going to teach you mathematics now. We're studying convolution. Everyone remembers this much? Yes. We did what did we do last time? We did composition of two convolutions. You remember that? It is composition of two linear and shift invariant functions or operations. Correct? And we saw that composition of two linear and shift invariant operations gives a linear and shift invariant operation. Right? So composing two convolutions gives a convolution. And we saw how to calculate the impulse response of that composed convolution. Okay? So let's start there. And let's say I have a convolution and it has got a spreading rule which is some numbers A, B, C. Okay, let me not specify it, but I'm going to say A goes one to the left, B goes straight down, C goes one to the right. Okay, and I'm composing it with another convolution. Let's say P, Q, R, S. Okay, this is okay. Now, how should I say this? These two are going to collapse into a single convolution. Correct? I'm going to ask you to calculate the impulse response of that convolution, but we'll be lazy and just do maybe one of those calculations. So let us say I put in an impulse input like this, and I ask you to calculate this output here for the impulse input passing through these two convolutions. Do it. By now you should be like signal processing pro max, like you should do this in like 15 seconds.
BR plus CQ plus AR. BR plus CQ plus AR.
BR plus
CQ
CQ
AS.
plus AS is the calculation. I don't know. I haven't done it yet. Who agrees with him? One person agrees with you. Two people agree with you. Three people agree with you. Seven people agree with you. Seven people going once, seven people going twice, 8 people agree with you. Okay. You're going viral, man. Huh. Any other answers? I don't know. Let me see. BR CQ AS. Seems so. Okay. Why was there no P? Yeah, because this line here seems to be 0. And so, yes, there is a P, but you don't see it because that line there is 0. I'm going to ask you to do another sum here. PQRS ABC. Okay. And yes, 0, 0, 1, 0, 0. And I ask you to calculate this output here. Okay. Good, good. And what is the answer?
SA plus RB plus
SA plus RB plus QC. He just doesn't want to make it too obvious. But yes, what do you see? Then it is the same. Okay? Yes, the same number, right? Seems to be the same number. What do we seem to be on the verge of discovering right now? Order of composition doesn't seem to matter, is what is how we put it, right? Let's be a bit more specific about it. Okay, let's be a little bit more specific. How about just calculate this quickly? What do you get? You can calculate convolutions by now, right? I mean, should be, yeah. Calculate this. I mean, it's just the next output of
BS plus C.
BS plus C. It is
BS plus CR.
Sorry, BS. Yes, BS plus CR. Let's calculate this output here. SB plus RC, correct? Huh? Now, assume for the moment that you have convinced yourself that all these numbers are going to turn out to be the same. Okay? If all these numbers are going to turn out to be the same, what does that mean? That means that both of these systems have the same impulse response. And of course, each of them is a composed convolution, which means each of them is a convolution. Which means these are both convolutions with the same impulse response, which means they are both convolutions with the same spreading rule, which means they are the same convolution. Okay? And hence, as you said, order of composing convolutions doesn't seem to matter. We'll make it a bit more precise in a moment, but write down till here the argument that I just said.
Order of? Can you repeat the statement?
Write down.
The one before that. Order of. Starting with order of.
Order of composing convolutions does not matter. Compose convolutions in any order, you get the same. What should we say? You get the same convolution. Right. Okay. Now, mathematically, oh, by the way, okay. So, are you convinced that this will always happen? It will happen. I mean, all the numbers will be the same, and even if I add more lines, it will be the same. Are you convinced of that?
Yes.
What can someone give me a quick argument about why? Why essentially this number and this number will be the same? The question is, can someone give me a quick argument regarding why the number here and the number here will be the same? Yes. It is basically, see, so this anthill is at some index, right? This anthill is one index to the right. Okay? And the question you are really asking yourself is, what are all the paths to go from here to here? Correct? And you multiply all of those paths and you add up the result, and that's the answer here. Correct? So one of those paths is this path, B R. Correct? Another path is, say, this path. What is this path? P Q. How do you know the label here is Q? Spreading rule has to be the same. Okay? Only then you call it a convolution. Otherwise, you just call it a linear function, right? Because there is just a network, which means it's just a matrix. Correct? Okay. And what's the third thing? AS. Another color. AS. So these are all the paths to reach here from here. And here, if you try to see what are all the paths to go from here to here, you will see that there is so this path here, let's say, this path is the path RB, right? But you are trying to find all paths at a particular displacement. So which means that the displacement here is how much? By an address of 1. Correct? So you have to find all paths that together produce that displacement. Maybe one of them produces a displacement of 1, the other produces a displacement of 0. Or the first one produces a displacement of -1, then the other one has to produce a displacement of 2. Correct? Now this path here is producing a total displacement of 1 by doing a displacement of 1 before and then doing a displacement of 0, and its numbers match these numbers exactly. And for every path here, there is going to be a matching path here, because all you need for a path to because all you need for paths here is that the total displacement should be 1. Correct? Since the total displacement is the sum of two individual displacements, and the sum is commutative, it doesn't matter which displacement you do first. Right? And which is why the numbers here are going to be exactly the numbers here. This is okay? Formalize this nicely on your own. And as you have realized by now, the homework will ask you to formalize this. Any questions here? Right? Same thing will happen at a displacement of 2, at a displacement of 0, at a displacement of -1. At any displacement, the same thing will happen. Same thing will happen how many ever non-zero lines you have. Okay? And hence the impulse response of the two systems is always going to be the same, which means that the convolution is always going to be the same convolution. Now, if instead of 0, 0, 1, 0, 0, the signal that went in was some x, the same signal x went in here, do you agree that what will come out of the composition is going to be the same signal? Why? Because it's a convolution with the same spreading rule. So if x goes in, then the same thing has to come. Correct? What comes out here? Okay, let's give this spreading rule some name. Let's call this f. Let's call this g. Okay. What comes out here? X star f comes out on the middle line and then spread according to g. Correct? And that has to be the same as what happens here? X star g, because this is g spread by the rule f. Okay. Oh, but wait. This equals what? X star S star g, correct?
Yes.
And this equals what? X star
Star F.
g star f. Yes, this is by associativity, correct?
Yeah.
And so sorry, so all of these are equal, and so this is equal. And so x star f star g equals x star g star f. Isn't that exciting? That means that f star g equals g star f. Okay? F star g equals g star f. What should we call this? Commutativity of the convolution operation. Yes.
How we went from there to there,
From where to where?
from like we know that x star g is equal to x star g star f, but then from there to show that x star g is equal to g star f, don't we also need to see that the map is bijective? I think we.
And he doesn't understand how we went from here to here. There are two issues here. The simpler one is mathematical. So at least mathematically, who sees how to go from here to here?
Using the impulse response. Impulse response is the convolution.
This is going to be true for any x,
Yeah.
right? Put in x, the impulse input.
Yeah.
And what will you get? You will get S star G as a signal come out. If you put it, but for the equality, you have to put in an impulse input here. What you will get G star F, the signal come out. Since these are performing the same operation, the same signals have to have come out. Which means that the signals F star G and G star F have to be the same. That's how we prove. Correct? Mathematically, this is fine.
Yeah.
Is there any other kind of unease that you feel with this? Because I feel very uneasy when we get here.
Like we were having like we asked the question a while ago regarding some like so in that we are getting the output as a vector, right? And I think this is a statement about convolution.
See the problem here. Let me show it in another light. Okay, it is not a mathematical problem. It's a bit of a philosophical problem. You remember we were doing these anthills. And I don't know, some 2, 4, 8, 1, 6, okay? And there was some spreading rule, 0.1, 0.8, 0.1. And this would have produced some output, correct? Now, I can draw this picture. Point 1, 0.8, 0.1. Do you see this?
Yeah.
And spread it according to the spreading rule 2, 4, 8, 1, 6. And that will produce the same answer. Okay.
So point being that the context doesn't make sense here using this.
Yeah. Say that again and say it better.
I need to think. I'm sorry. The mathematics is not able to describe the context well.
Do you see that the answer for both of these will be the same? Correct? This is what you prove. It's just maybe one of them seems nonsensical. Right? I mean, what does it even mean? So,
Then we can give input as a signal, convolution also as a signal. So it's just signal convolute signal. It's not really that clear. If you think of all of them as signals, if you think of them as input and output, then it gets clear.
correct. Agreed. And so, this is the kind of trickery that we are going to have to get used to. Okay. So, when I say F star G, it was supposed to be F spread according to the spreading rule G. Okay. Then I said a little bit, but to remember the spreading rule, I just have to remember a sequence of numbers. So we will reuse the idea of a signal to even remember spreading rules. That's how we will be able to say spreading rule and impulse response is the same thing because their types will match. Correct? But still, in our mind, some system was operating on some data. Okay. So, in our mind, this was the data, and this star G was the system operating on it. Does this make sense? F was the vector, star G was the matrix that operates on the vector. It's the linear function that operates on it. Okay. Another viewpoint is, as he's saying, is don't think about it this way. This is F is just a signal, G is another signal, and they convolve. It means whatever it means. It's just a mathematical operation. Don't think about a system and a physical phenomenon going into the system. Don't think about it. They're just the signals. They convolve. This is the approach most textbooks take. And so they don't worry about this, but we will have to worry about this because we didn't start with that approach. Okay. I think I think we have to learn both of these approaches and we have to learn to switch between these two approaches because there will be opportunity for us to beneficially view convolution as a linear system, which means as a matrix. In which case you are thinking of this as the signal F going into the linear operation star G. But we will have other opportunities where it will be better for us to think of the same thing as a signal convolving another signal. Okay, and we'll have to be able to switch our mind between one approach and the other. Very strange. You have F and you have G. You can think of F as the vector and star G as the matrix, but you can switch them around and think of G as the vector and star F as the matrix. Okay, this is strange. This won't happen in normal linear algebra. This is like a special thing that is happening because we are doing a special kind of linear algebra, which is shift invariant linear algebra. Okay, write this down. No question? Question? Anybody?
What does convolution mean when we are saying signal F is convolving with G? Like we said, we have a spreading rule which spreads out the signal, let's say. But when we say signal X convolving with signal G, relate or
I mean, so really, one way to think about your question is what does star itself mean?
yes.
Right? And star, so mathematically, you can think of star as an operation which takes in two signals and produces a signal.
Yeah.
Okay. And how does it do it? It uses that formula that we use, that we wrote at the end of the first lecture. Where did the formula come from? Doesn't matter. Okay. In this viewpoint, when we as an applied mathematician see a linear and shift invariant system, we will model it as a convolution. Now means we will model it using the convolution operator star with a fixed impulse response, which is just a signal now. Okay. And there are possibly other uses of convolution also, which we haven't learned till, where the signals mean other things. And we will see such uses later on. Okay. So, on its own, star doesn't have a physical interpretation. It has a mathematical interpretation, which is just, this n equals summation over k. This, that's all. Okay. It's a purely mathematical construct, and this is what it is. Does that answer your question? It's not a very satisfying answer, but that's the answer, right? Going into the realm of mathematics and application, you are going to get these strange things up. Any other questions? Is it okay? Huh? Have you done calligraphy, guys? Anyone done calligraphy here? Where is it? Did you do like a broad nib calligraphy? You did? You also did? Anyone else? Like, for example, if I want to, I'm sure you've seen these kinds of fonts, right? If I want to say, write my name in a calligraphic manner, let's just do initials. Name is too good. I don't know. Let's see. Have you seen these kinds of fonts? Where you are using like a slanted nib. Usually a pen, I'm trying to do it with a chalk. Usually a broad nibbed pen, and you do calligraphy. Nice, no? How else could you do this? Imagine I had a very strange kind of a pen where the nib is in the shape of the letters U and K. The nib is in the shape of the letters U and K.
Drag it.
It's a stamp, but it's thin letters. And what could I do?
Just press it and drag it.
Yeah, I could take that nib in the shape of the letters and drag it to produce the same result. Correct? Right? But I mean, imagine now there was an alien whose name is the symbol slant and who does calligraphy using UK shaped stamps. For that alien, the symbol will end up looking the same but will mean something very different. Yes? Anybody care to continue the lecture from this strange place? This is how we can do convolution. Why?
For someone with the signal person, maybe
your point being that you're trying to make a less interpretable signal into a more interpretable signal by using convolutions.
Maybe. Maybe. I'm going to be surprisingly literal about this. Give me a moment. Huh? Does everyone know images? Do they still exist in the world?
Depends on the
Images have what? Pixels. Nice. Images have pixels. So imagine an image with these pixels. Okay? Hmm? Now, what are pixels? Pixels are just small locations with some value in them. So now imagine your mind small antils. Okay. Some of those antils have more sugar, some of those antils have less sugar. Okay. Right? There are rich antils here with lot of sugar, and there are relatively poor antils. Okay. You see this? Okay. Now, if I were to produce this signal in a calligraphic manner, what is the spreading rule of that calligraphy? I'm back to normal calligraphy, not alien calligraphy. Normal calligraphy, the slanted nib calligraphy. You see that slanted nib calligraphy, stay with me, slanted nib calligraphy takes a point and spreads it into a slant.
yes.
Correct? And so you can represent calligraphy as a convolution. Now the convolution is happening on a signal which is like this. Okay, but hopefully you understand this. Okay. So what is the impulse response of slanted nib calligraphy? It's going to be the slant itself. Right? The pen is the system. If I just put the pen on paper and take it out, what will happen? This is what will happen. So that is the impulse response.
Wait, is it the impulse response or the input? Is it the impulse response or the input?
This is the impulse response. Right? And when I convolve these with each other, I get what? What will happen? Think about it. This is the rule by which I am spreading the wealth existing here. So what will happen is this wealth here will get spread like this and like this and like this and like this, and you will end up getting this. Okay? And if I had a UK-shaped nib, then what is that? The impulse response of that? This is the impulse response. Why? It's a stamp basically, right? Like someone said, you do this, you get this directly. And if I move it in the slant fashion, I will get the same answer. Commutativity of convolution. Does it make sense? This is true literally. I am not being philosophical. This is true literally. I don't know. I know many of you are part of the image processing course. I may have, taught something that he has yet to teach. But there is such a thing as image convolution. You can work it out on your own. This is how it works. And we just saw commutativity of image convolution. What we are calling impulse response, image processing people call it point spread function. Everything works in a very similar. Okay? Here is Brutus. Here is Brutus. Caesar is seeing everything double. What is the impulse response of seeing everything double? Two dots. What's the convolution? Two bruti. What happens later in the night? No, that happens the next day. This is a scene from the previous day. It happens between Acts 2 and 3. Later he sees two stars. Everything he sees, he thinks is Brutus. What's the impulse response of that? Brutus. What's the result? Commutativity of convolution. Write down whatever you want to, and then we'll start some talk. Let us say there is some function, let me say f of alpha equals a alpha square plus b alpha plus c. All these symbols are now so overlaid that I need to explain to you what is happening here. Very simple things are happening. Alpha is a number. F is a function that takes in a number and produces a number. A, B, and C are also numbers. Multiplication and addition are happening with numbers. Something very simple is happening. Okay? Nothing, no need to worry about signals, vectors, matrices, nothing of that stuff. Just simple high school algebra is happening. Right? Oh. The question is, what is the alpha where the value f of alpha is the minimum? Simple high school algebra, you might even know the answer. Even if you don't, you can calculate it in a minute.
Are ABC positive? Or positive? A, B, C.
So that's a good question. Are all of them positive? Are A and B and C positive? What do you really need to be positive? You need A to be positive for this to have a minimum. If A is negative, what will happen? Yeah, it will have a maximum, but it will not have a minimum. Correct? This is simple high school maths that we did. If you draw a graph, it's a parabola, right? Parabola is curving upwards if A is positive, it's curving downwards if A is negative. Correct? And then, what is the alpha for which f achieves its minimum? So, minimum achieved at alpha equals minus b by
2a.
2a. Why?
Take the derivative and set it to 0.
Take the derivative and set it to 0 is one way to do it. Okay? Or
It's a coefficient.
is there another simpler way of doing it? Do that. F of alpha, which equals a alpha square, sorry, a alpha square plus b alpha plus c equals what?
The coefficient of alpha we can multiply and divide by a and times c.
Multiply and divide by a is what you want to do. Okay, we'll humor you and we'll do this. A alpha square plus b by a alpha plus c by a. Okay, and then
8b by 2a whole square and subtracting.
and you will get alpha plus b by 2a the whole square plus c by a minus
b square.
what happened?
B square.
B square by 4a square. Okay, correct? And now if you look at this term does not change with alpha. Correct? So it will have no effect on where the minimum is achieved. And this term is a square, so the minimum value it can achieve is 0. Where will it achieve its minimum value? When alpha plus b by 2a equals 0, which means when alpha equals minus b by 2a. And hence, the minimum of the quadratic function is achieved at alpha equals minus b by 2a. Correct? This is the fact that we will need later on. Let's take a 6-minute break. Please come back exactly at 6. So suppose I am speaking something, just for the sake of argument. Suppose I am speaking something. Let's say that he is hearing me. Okay? Suppose, for the sake of argument, let's say he is hearing you. Now, what are the we have seen this before, right? There can be very complicated things happening. He can hear me directly. He can hear me through lots of echoes. Okay. Remember this? For the time being, let's disregard the echoes. Okay. Let's think that he hears me only directly. Okay. Let's further simplify to say that there is no time delay. Negligible time delay. We'll say there is no time delay between me speaking and him hearing. Okay, I'm setting up a situation. You have to understand it carefully. I'm speaking something. He is hearing it. There are no walls to reflect, so he is hearing on top only directly, and there is negligible time delay. We'll disregard the time delay. So he hears it instantaneously. Okay. Still, he doesn't hear it at the same level that I spoke it at. Okay. He is hearing at probably at a lower level. Okay. We are simplifying the situation compared to before, but we are going to also make it a bit more complicated as well. I'm going to introduce a new part of the problem which didn't exist before, and that is the door. What is the door doing? it's creaking. Okay, I am speaking, he's hearing, the door is creaking. Okay, there is no time delay, there are no reflections, but there is an unknown amount of yes, there is an unknown amount of noise. There is also an unknown scale that he hears my speech at. Okay, he doesn't hear it at the same level that I spoke it at. He hears some scale of it. Under this situation, our problem is going to be to try to estimate the scale at which he hears my speech. Okay, very interesting. If I am able to estimate very well the scale at which he hears my speech, then what will I be able to do? Understand it. Nice. That's why you always do things. First thing is understand. Another thing you'll be able to do is subtract it from what he hears. If you knew the exact scale at which he hears me speaking, and you knew my speech, then you will be able to subtract that speech from what he hears. And then what will remain in what he hears? The door. And so for some reason, if he wanted to concentrate on the door, he will be able to do that. If he has more interest, if that's a better lecture, then he'll be able to concentrate on the door. Okay? And disregard me. By the way, our brains seem to have the ability to do that. Concentrate on the door or concentrate on something and disregard other things. It's a very complicated version of a very simplistic problem that we're trying to solve right now. Okay? Is it okay? So we have with us two signals. One is the speech, one is the reception. Okay, the transmission and the reception. The reception has an unknown scale of the transmission, and the reception has also added another signal, which for the sake of argument we call noise. Okay, unknown scale plus added noise. I'm going to so how do you what do you mean by speech is a signal? Where are the numbers? Where is the sequence? Where are the ands? How is speech a signal? I said this before, but let's now be a bit more precise. How is speech a signal?
You can quantify it in different ways.
Okay.
Taking any metric you want, like the intensity of the or pressure, for example.
Okay. I like pressure, so let's do pressure.
Pressure of the air with time is changing, and if you take, say, you spoke for 5 minutes, and over that 5 minutes you have discrete time steps, you have certain pressure levels at the where the sound is, and that's how you have a signal which is 5 minutes.
Okay. And what are the discrete time steps that you will take?
That depends on how fast you are changing your sound.
And how fast I am speaking. Some people say I speak too slowly.
Or
You don't need a lot of time steps.
Or you can base it on the person listening, because humans can register a change in pressure for only some amount of some milliseconds.
Okay.
You can take that as a basis.
Okay. So yes.
Will we solely rely on one metric for calculating, for converting speech into a signal? Because there can be a possibility that one signal can mean two different things, right? If we just use a pressure.
Yes. And so for the time being, we will rely on one measurement. And you are right. Maybe we should do more complicated measurements. And yes, if you are doing something advanced in your thesis or PhD, then you might be doing multi-measurements and trying to reduce noise using that. And there's a lot of techniques like that. We're studying this for the first time. So right now there's one measurement. So we'll stick to one pressure that is changing across time. Okay. The point I'm trying to make is as follows. To some idealization, speech is a changing pressure signal, changing with time. Okay, it's a pressure that is changing with time. And in that sense, it's a continuous signal. Okay, so the time axis is a continuum. Okay, time axis is a continuum, and speech is like a graph of pressure drawn on that time axis. Does this make sense? Change the pressure that changes with time. Correct? Now, of course, such an object will have how many values? It will have infinitely many values because the continuum is made up out of infinitely many points. And you cannot calculate that in a computer or even by hand or whatever. So, we are going to have to reduce that to a discrete number of times. Okay? That is where the time step that is referring to the discretization comes from. In signal processing terms, this is called sampling. Okay, where you sample the signal once in a while and you convert it into what is called a discrete signal. Okay, so technical terms, discrete signal, continuous signal, discrete signal, and sampling. That is the. There's a lot of theory to be learned in sampling, but we will not do that. Do that later. Continuous signal, discrete signal, and sampling. Okay. Now a space. I mean, even a sampled signal is infinite. So,
What exactly makes the signal continuous versus
it is whether the signal occurs at discrete addresses or a continua of addresses. So the anthill signal was a discrete signal because the anthills are discrete from each other. Okay, but
sometimes we already at a finite time step or continuously changing.
what is
Changing continuously or changing at a discrete
what is
signal.
a signal? So a continuous signal, if it is a time-based signal, is changing continuously with time. And a discrete signal takes on values only at discrete intervals. There is no meaning to what is its value between two intervals. Okay.
Sampling is looking at the discrete point.
Yes. This is okay. So sampling first, people thought that speech signals, how fast should we sample them? They thought that, oh, let's do many hundreds of samples. That was not enough. Then they thought thousands of samples per second. For a long time, they were doing 8,000 samples per second. Then they started doing 44,000 samples per second. And they thought even that's not it. They did 48,000 samples per second. Then they went 96,000 samples per second. They seem to have settled there for the time being. So people are doing these days for speech signals 96,000 samples per second. That's a lot of samples in 1 second, but it's still discrete. Okay. So now in our problem, when I'm speaking something, he is hearing something, door is creaking. Let's assume that these are all sampled, which means discrete signals. Okay. I will tend to draw discrete signals like this. So this is your time axis, which is discrete. Okay. Okay, time axis or signal independent axis, whatever it might be, but usually time. And what do these heights signify?
The property I'm measuring.
The property you are measuring, right? The height signifies the property, so it is like a bar chart or a graph basically of the signal. Okay. Okay. So now let us say that this is what I spoke. We will label it with my initial. And then let's say that this is what he heard. Label it with his initial. Are they? X stands for anything, no? Algebra. Okay, he accepted. Okay. Now, what are we trying to do? We are trying to find what is X made up out of. We are trying to find what is X made up out of. It is made up out of some scale of U plus some noise, correct? So, here is one way to think about it. Let us try to find the scale of U that comes closest to X. Okay? Understand what I'm saying? Try to find the scale of U that comes closest to X. Maybe, so draw this U. I'm showing only 4 samples, okay? Even if I spoke for 10 seconds, that is 9,60,000 samples, but I can't show those many on the board, so I'm showing 4. Maybe there are more samples. Let's not worry about that in my representation. So draw this signal, and maybe draw a few of its scales. Draw it, just draw it. Negative scaling is allowed. So if this is U, then this will be, let us say, this signal in pink will be half U, correct? And then you can imagine like 1/10 of U or double of U or all of these various versions of U. From all of them, we are trying to find the one that comes as close to the values of X as possible. Okay. Will one of those scales fit X precisely? Why not? Yeah. In this case, it won't, because that's how I drew it. So it will never happen. But from the point of view of the story, why not?
Noise. They should be scaled uniformly. They should be scaled uniformly, right?
Yes, they should be scaled uniformly. Yes. From the point of view of the story, they are being scaled uniformly. So, like, I am not moving around. Whatever is the scale between my speech and his hearing remains the same. Noise doesn't have to be, I mean, there's no such thing as noise is being non-uniform. Noise exists is the reason why the scale will not fit perfect. Because there will always be some added noise. Constant, as in a constant. So, let's say a value of plus 2 across. Then it will fit. Really? It should be. If it's plus 2,
You can't scale like that too.
no. When will it give you the answer? Yes, if the noise was itself proportional to u, then this will still be a scale of u. That's true. But then, like, that's like when the door is giving the same lecture that I am giving. And we are going to say that that's unlikely. So that is not going to happen. And we'll leave it at that for the time being. We can't make it more precise than this. Okay? And so that is not going to happen. Okay? Door is not giving the same lecture as me. So, and that means that no scale of u is going to fit x perfectly. So if there is some scale, let us say some scale a of u,
Sir,
yes,
what if we multiply it and then divide it?
multiply it and then divide it.
Yeah, I think then can we not go to x from u to x? Or will that be a little problematic?
Explain that better. What do you mean by multiply it?
So let's say now you're looking at one of them is down, right? So one of them is facing down, correct?
Yes.
In u.
Yes.
Now you multiply it. You multiply it to the point where it increases a little like this. Okay? In the graph.
Okay.
The others will also scale up.
How?
I mean, you're multiplying it, right?
Yes, but you have to multiply all by the
Same thing.
same scale.
Yes.
So if you multiply something by a number which caused it to flip, what will happen to everyone else? They will flip. Okay. So yes, you can scale with a negative scale, but that flips the whole thing around. Okay. Right. So, I mean, think of AU is some scale of U, and let's try to draw that AU here, and let's say that looks something like. Okay. Then what is the noise?
The difference.
The difference between the two is the noise. Correct? The difference between the two is the noise. And so, if I were to say that the noise is N, I represent noise by the letter N. What is N? X minus AU. Nice. Again, think about this carefully. What is U? Mathematically. What is U? U is a signal. What is A? Scalar. We can use the word here. Scalar. The number. What is this operation between A and U? Scaling. Right? What is this operation minus? Element-wise subtraction of signals. And that gives out another signal. Okay? Or you can think of the whole thing in vectors if you want. This is vector scaling, this is vector subtraction, which is element-wise subtraction. It gives out a vector. Yes.
Here we just assume that we somehow found the A.
No, we can't. But while many a times while doing mathematics, we assume we know something we don't know yet, and then derive properties of that thing, and then hence we find that thing. That's how we do algebra, if you remember. That's where x comes from. I don't know what that number is, and let me call it x. Let me do something. Finally, I gain enough information that I can actually calculate it. Right? That's how you do algebra. The question is correct.
So we know the noise, like the exact noise.
No, we don't know the exact noise. We know what I spoke and what he heard.
Okay.
And that's a problem. It is a problem. And I'm going to talk about it. You're right. Okay? Is it okay? So, what he is possibly pointing to is correct. That is, if I know n, then I'll be able to tell what a is. If I know a, I'll be able to tell what n is. But in the story that I am telling you, we know neither n nor a. We know x and u. Okay? So, hence, we are going to come up with a heuristic idea, which is as follows. Find the a that fits x the best. What does that mean? Find the a that leaves the least noise. Okay? Okay?
So you said we know u, which is the original signal, but in most contexts we don't know u either because we measure a signal, right?
Yeah, yeah. So, yes. Mhm. And so, in the current story, there is a microphone at u, and there is a microphone at x. So, in this version, this is actually this same game you play with different microphones and say this is known, this is unknown. You keep on doing this, and that's the entirety of signal processing, basically. So we solve something, we learn something, then we try to solve something else. So you're right. There will be other versions of this problem. Okay. Yes.
You always want to do linear things, like because you can always do it with very non-linear things, so something or something like it equal to v equals to x.
Yes, but I mean, we are assuming that acoustics is creating some linear scale, which means some scale between my speech and his reception. We are assuming that about the physical system, and which is why we are not going to something strange. Okay? Is it okay? Once again, so our idea is going to be to try to find a that leaves the least n. But what do you mean by leaving the least n? What do you mean by least n? Right? N is not a number. What is n?
A vector.
N is itself a vector or a signal. So how do you leave a least signal? You have to do something, right? I mean, you want, okay, what would be ideal? What would be the best fit? If all the values of n were 0, that would be like the best. Correct? So when you say least n, you want the values of n to be as small as possible. But small in what sense? You want them to be as close to 0 as possible. Okay? And so you need to come up with some sort of thing that you are going to minimize. Okay? Now, you suggested mod. But mod, why mod?
It's a vector, so it's
Oh, that mod. That's not called mod. That's that is called mod, what you just said. Okay. Try not to use, like I said before, try not to use terms that I haven't introduced yet. Because, as you must have realized by now, some of my terms will match the textbook and some won't. So, okay. So, okay. So, if you want a bunch of numbers to be as small as possible, one way to do it is to calculate the sum of their squares. Why do you take squares? Because a square is a positive number, whether the number itself is positive or negative. So, A square is minimum for which number? 0. Square of 2 is 4, square of minus 2 is also 4. So square of 0 is the minimum, right? But you have a lot of numbers, so you take the sum of the squares of all of these numbers in n. Okay? And that is the value that you want to try to find the minimum. Okay? So what is the value? What is that value? Sum of, let's say, k going from minus infinity to infinity. It doesn't have to be minus infinity to infinity. I mean, maybe the signal is terminated. Here, there is no convolution right now, so we don't have to worry about indices. Okay, but I still use minus infinity. And n k square. Correct? Correct? And so what is your problem now? Your problem is to find a that minimizes this number here. Okay? Next step. What is the k? What is nk? Nk is the kth number in the sequence n. Or now we can say the kth sample of n. Okay, the kth sample of n. Okay. So what is the kth sample of n? Xk minus auk. Why not akuk? A has to be the same scale. In fact, if I allow different scales everywhere, then I'll be able to match it precisely, correct? Right? So AK, not AK. Okay? Do it, write it, write it. Write the next step. What's the next step? There's only one thing to do here. Do it. Expand. Huh? Let's follow the rabbit for a few steps and then we'll discuss what has happened. Xk squared minus twice a xk uk plus a square uk square. Correct? Okay? Next step. There's not many things you can do. To do what you can do. You do what you do. That's one or two things before that. Separate out the summations and bring out the things that don't depend on the summation. Right? What doesn't depend on summation? A doesn't depend on the summation, right? A doesn't have a k in it. And so A can move out of the summation, correct? The summation over A. So what do you write? So this equals summation over K xk squared minus twice A summation over K xk uk plus A squared summation over K uk the whole square. Correct? Okay? This equals this. Are we okay? What's the problem? Find A that minimizes this. Find A that minimizes this means now find A that minimizes this. How do you find A that minimizes this? Yeah, it's that, isn't it? Correct? Because these things look complicated, but they are just capital A, capital B, and capital C from that part of the board. Correct? This is just a quadratic function of A. Yes, this thing, only A is changing. So it is a quadratic function of A. So find A that minimizes this. Is just do that thing there. And what is the A that minimizes this? So basically, here, it's A alpha square plus B alpha plus C, right? So A, capital A, is this term here. Yes? Capital B is what? Minus 2 times this sigma here. And capital C is this term. Capital C doesn't matter because the formula doesn't even have capital C. And so you get A equals minus B by 2A. So that is minus this upon 2 times this. Correct? Right that? What do you get? Summation xk uk my summation uk whole square. Okay.
I had a doubt, not about now, but if and we are saying that we are trying to minimize noise, but in the example which we discussed, noise is something separate.
Yes.
So so we are in a sense minimizing the effect of noise, not the signal itself.
Let me, right now I'll be able to just say that this is a heuristic attempt at finding noise. Okay. Think about it this way. As much of the signal X as can be explained by you should be explained by you. Whatever remains is the noise. Is how we are, is our heuristic idea. When we say that the door is not lecturing, so right, whatever it is of the lecture that he heard must be the lecture that he heard. Whatever remains must be the noise. Is a heuristic. Okay. And in fact, it will not be precisely true, but there is I can't say more than that right now. There is a very deep statistical analysis of this, but that's inaccessible to us right now. Maybe we'll reach it at the end of the lecture. Okay? So right now, just think of it as a heuristic. You are right. You don't know if this is the exact term. This is our attempt at recovering n. Okay?
But n is a constant, right? It's not something that changes. I mean, we can get different values of n, but
Okay.
in reality, n is the fixed value.
In reality, n is a fixed actual physical phenomenon. But our estimated n depends on
Yeah.
E. Okay? Good questions. Is it okay? Now, there is a certain way of writing this as follows. Okay? I'll explain this in a moment. New mathematical symbols. I'll explain them in a moment.
X.
Yes, okay. Okay is the thank you very much. There is a certain mathematical way of writing this same thing. Okay. In general, this symbol here, with the left bracket, the comma, and the right bracket, angle bracket, left angle bracket, the comma, and the right angle bracket, is called the inner product. Okay. And what is its definition? In general, if you have two signals, let us say P and Q, the inner product is just sum over K, Pk, Qk. Okay. Is it okay? This is one of the mathematically very often used thing. It occurs everywhere, from Euclidean geometry to quantum physics. This thing happens. Okay. Basically the same thing wherever. Sometimes it's called the dot product, called the inner product, it's called the quantum bracket notation, quantum Dirac bracket notation, many different names. Is it okay? And so then by this definition of the inner product, do you agree that this formula could be written like this? In signal processing terms, the inner product is also known as correlation. Okay. Correlation. This thing, you take two signals and do this thing, it's called correlation. And if you think about it, it's kind of, and this thing is supposed to tell you how to make u as close to x as possible. So, and the only computation between x and u actually happens here in the numerator. So the numerator is kind of telling you some correlation between x and u. That's where the word comes from. That how similar are x and u is what that is. I'll explain this better in a moment. Is there a simple way of seeing why there is a u in the denominator? Normalization. What does that mean? Why? What are you normalizing against?
It's against the difference.
In what sense?
Whatever correlation there, we are trying to convert it into a percentage of fraction.
Yeah, agreed. Agreed. So think about it in the following fashion. Let us say u was not this signal but exactly double this signal. Okay? Let us say u was not this signal but exactly double this signal. What is the best scale that will fit x? The best scale should be the same scale. Visually, it should be the same thing, right? Because the original u and the w have the same set of scales, among which you are choosing one scale. Correct? So visually, you should still be getting the same thing. But as a scaling number, what is that scaling number? If u is double of what it was before, then what is the number that you have to now scale by to fit x as well as it was fitting before? Half. Correct? So if you scale u by 2, then your scaling number should become half. Oddly, if you don't take this denominator, if you scale u by 2, what happens to the numerator?
Double.
It becomes double.
Hmm.
Right? Look at this formula here. If I double one of those signals, what will happen to the answer here? It will become double. So this numerator, if I make u double, it becomes double. But I want the scale to become half, which means I have to do something that divides by 4. And this u inner product with itself will become 4 times if u becomes double. That is the normalization. That is the correction that the denominator applies. Is this like intuitively okay? At least?
Why do it have to be half? If we double it, x is also good. Double.
No. X is what it was before. X is exactly what it was before. And let us say u is double. Then what scale of the new u will fit x the best? The same x the best.
Can we say that it is used to make the signal scale invariant? No.
No, this is a very different idea. No. We'll talk about this after class, but no. Yes.
Is there assumption of noise being less than the original signal in all these calculations, or like at least for this heuristic, or it will work even if the noise is?
There's an assumption of the noise not being like the signal. I haven't explained that better because even right now I can't, and I will in a minute. Okay. Okay, so that is what that is doing. If you think about this geometrically, what is u? U is a vector. Let us say it has these 4 samples. So then it is a vector in what kind of geometrical space? In a 4-dimensional space. Okay? I can't really draw that, so I will drop a dimension and say that, let's say that this is a 3-dimensional space, and let's say that U is some vector in a 3-dimensional space. Okay? In some dimensional space, but I'll be able to show it in 3 dimensions because otherwise I can't draw geometry beyond 3 dimensions. Is this okay? What about X? X is also some vector in the same space, correct? Same amount of recording, otherwise you will not be able to do any of this. So in the same space, you have another vector X. Okay, let's say it's this vector. Is this okay? Where are the scales of U?
Straight line joining the origin and the tip of the
Correct? All points here are scales of U. Is this okay? Even here, all points on that straight line are all scales of U. Does this make sense? Correct? Like the AUs for different A's. Do you understand this? This is not just okay. Again, this is not just some hocus pocus thing. The numbers in those U's are actually present in this vector here, right? So there are these 3 axes right now. The first component of U will be the first number. The second component of U will be the second number. The third component will be the third number. If there was a fourth component, that will be the fourth number, and so forth. Okay? So that is that vector in some high dimensional space. Okay? And then if you are scaling it by some number A, that means each of those components is being scaled by the same number. And so what will happen to the vector? It will grow in the same direction or shrink or go in the opposite direction, but it will all be in that same direction. In fact, the definition of the word direction in vector algebra is all scales of a vector. Okay? This is okay. And among all of these scales, you want to find the scale that
Matches X.
matches X, but no scale matches X. X is outside. So you want to find a scale that then comes as close to X as possible. Correct? Right? Let us say I took this as A. I mean, this is AU, let us say. Then what will be N? This will be N here, correct?
Yes.
Agreed? Whatever remains. And what are we trying to do? We are trying to find the N that is the smallest. Geometrically, what is that? Perpendicular, yes. Okay. So everything that we did is actually this geometrically. Dropping a perpendicular from a signal onto the set of scales of another signal. Okay.
Aren't we dropping U on that dimension?
Are we dropping u on x or are we dropping x on u?
I think the way we have done it, we are dropping u on it.
Are we?
X on
It's x on u. Oh, I don't think so.
In the sense that we are trying to find the scale of u that comes closest to x. What do you mean by dropping perpendicular, right? I mean, just forget the axis and everything. You have a point, you have a line. What is the point on that line that comes closest to a point outside?
Yeah, that is clear.
The perpendicular, right? So where are the scales? The scales are scales of u. So the line is the line of u. The perpendicular is being dropped from x onto u.
Does it matter though?
no b and e. It's a different optimization. Like it will become bx minus u if you wanted to drop u onto it. Like optimize b such that
It
bx minus
matters a little bit if the lengths of x and u are not the same. And so you have to be a bit careful in saying dropping what onto what. If both of them are the same, if x and u are the same length, then actually you get a symmetry. Okay? But they are not necessarily the same length, which is why the denominator comes into picture actually.
From the signal point of view, you can say that x is getting close to u. Or you can say u is getting close to x. It doesn't make sense.
From a signal point of view, you are saying,
You can say either way around it.
but from the signal point of view, you are saying find me the scale of u that fits x the best. So you don't seem to be changing x, right? You seem to be changing u, at least that's how I am.
The scaling will be the same. The matrix, whatever the matrix will be, for the vectors is going to be maybe rotating around. It's going to be same, the negative of it. Also, in the vector form, there is only one vector to be closest. Independent of whether you use figure or
Okay, maybe let's do this as homework. What is the exact difference between I see what your point is. You are saying the same thing is saying. Dropping perpendicular from one to the other and other to the one are very similar, but they are not the same because the lengths of the two vectors need not be the same. So we will make this more accurate as a homework. Okay. Yes.
So to exactly match them, we will have to rotate them.
If we wanted to exactly match them, we'll have to rotate the vectors.
What does that mean in signal processing?
Right now, nothing. Yes. Right now, that is nothing that we know. Okay.
Is it a possibility?
Not on its own, but we will go to some theory later on, which is actually going to rotate signals in a very special manner, in a very high dimensional, very strange space.
What
Yes.
I'm saying when you're changing from point of view of u to x, we're not changing that we are going to drop the perpendicular from u to x. It's just the smallest line will drop the perpendicular from the beginning.
I don't understand what you're saying.
I'm saying when you're changing the point of view that we are going close, like when you're changing point of view from x to u to x, you're not changing that we are going to drop the perpendicular from x to u or u to x. It's always going to be one perpendicular. It's going to be either going to be from u or either going to be from. Let's suppose this.
But what? Okay, let's discuss it after.
Yeah,
This.
sure.
Okay. Yeah. Okay. And what can you say about n?
Yes,
Perpendicular to u.
completely uncorrelated to it.
it is both of these are correct. N is perpendicular to U, correct?
Yep.
Geometrically, we know that's where the minimum is achieved. Perpendicular means what? Like in coordinate geometry, what does perpendicular mean?
90 degree.
90 degrees in Euclidean geometry. And coordinate geometry?
So dot product is 0.
Dot product is 0.
Yes.
But what are we calling the dot product?
Inner product.
Inner product. So inner product is 0. And so at the minimum, what? At the A such that N is a minimum, we get that UN, the inner product, equals 0. Okay? Okay? This is known as the orthogonality principle. That N at the minimum is perpendicular to the vector that you are scaling. Okay? Or if you expand it, it looks like this. Okay? That's a very important principle in signal processing, and we are going to do lots of advanced uses of this principle. Right now, it just has come about. Do you see where this came from? I just took that N equals X minus AU, doesn't it? But then this is true at the minimum, which means I can substitute the value of A at the minimum. So I substituted this value, and that's where this came from. Correct? Okay. I like to remember this formula as follows. When you have taken all you can out of someone, you can't take anything. Okay. When you have taken all you can out of someone, you cannot take anymore. Does this make sense? I mean, the noise that remains, the error that remains between the two vectors should not itself have any component of you, because if it did, then why didn't you remove it? Correct? When you have taken all you can out of someone, you cannot take anymore. That's what this is saying. Okay? So, what we learned today was the idea of signal correlation, how it is important, how it solves a simple problem in signal processing. The homework will ask you to actually do this. Okay? And the orthogonality principle, which says that when you have taken everything you can out of someone, you can't take anymore. We are going to see the convolution version of this in future lectures. Because right now, we removed the idea of a time delay. Correct? Now, when you add back time delay and these complications, what happens? What is the variant of this that you get then is what you will see in the next lecture. Thank you very much. See you on next Thursday.